Good afternoon. I'm Frank Mand, a member of what we call grammatically the Plymouth Saltwater Intrusion Task Force. One of the task force's responsibility is storytelling. And today you're going to hear a few stories of the unseen and the obvious, of the nuisance and the nightmare, the everyday and the timeless. It's a story of little things which, if not paid attention to, can quickly evolve into world changers. Are we exaggerating for effect? Perhaps. But consider that saltwater intrusion can result in the loss of the species you expect to find, the forest you expect to see, the water you thought was pure, and then, bottom line, the taxes you might have expected to pay. That is in part why this project has a dozen partners. Each partner has a distinct concern. One partner, the Plymouth Water Conservation Committee, is trying to dramatically reduce the per capita consumption of water in Plymouth. If what we abbreviate as SWI takes hold, that effort will be more important than ever. We have the Six Ponds Improvement Association. They're another partner on this project, a community organization that works every day to ensure the beautiful ponds and wetlands that are the centerpiece of their neighborhoods retain their biodiversity, their vitality. The Herring Pond Wampanoag tribe, another partner, can't help but see threats like SWI as yet another insult to their homeland, which by definition is an insult to them. And then there is the municipality itself, call it partner number one, and by extension, the state government, who have partnered with us on this project because they know that they can no longer afford to simply react to the environmental changes happening all around us. As I say, we have a dozen partners on this grant, but we could have had many, many more because everyone recognizes that without good, clean water, life itself is untenable. So today you're going to hear the who, what, where, why, and when of saltwater intrusion. And then we'll take a brief side trip into SWI's effects on wetlands and coastal woodlands. And finally, we'll hear how what we've learned so far is being applied to coastal communities and in particular to Plymouth. We'll hear these stories directly from three accomplished researchers in this field. First, from Dr. Julia Guimond, a National Science Foundation postdoctoral fellow at Dalhousie University, who will give us the who, what, and where. Then Dr. Holly Michael of the University of Delaware will briefly focus on SWI's effects on wetlands and woodlands. Then our project scientific lead, Dr. David Boutt from the University of Massachusetts-Amherst, will go local in a presentation entitled Saltwater Intrusion Vulnerability Assessment in Plymouth, Compounding Effects of Sea Level Rise on Water Quality and Aquifer Sustainability. Also with us today to help answer questions is Dr. James Heiss, a professor in the Department of Environmental, Earth, and Atmospheric Sciences at UMass Lowell. So a first little apology of the day will go out preemptively to these accomplished academics because we don't have time to recount all the degrees, honors, positions, and papers that they've accumulated in their careers. We've provided a lengthier hard copy summary for those attending in person at the center, and we'll provide that as well to anyone online if they request it. Finally, if you have questions, we ask that they be succinct to allow us time to get in as many as possible, and that you wait until after the presentations to pose them to our experts. If you like, write them in the Zoom chat ahead of time. So, making sure you're muted, let's get started. And here to lay the foundation is Dr. Guimond.
Right. Everyone in the audience, I'll do the two-person thing. Let me show my screen here. All right. Can everyone virtually see and hear me? I can't see you. Yes? Can those online hear me?
You're good. Yep.
Okay.
Julia.
Okay. Hi, everyone. As Frank said, I'm an NSF postdoc fellow, but I'm actually not located where Dalhousie is in Nova Scotia. I'm down the road in Woods Hole. So I'm really excited to talk about these issues with you as a local, as somebody who lives near the coast in Massachusetts as well. And so I'm just going to give a pretty broad overview of what saltwater intrusion is, why it's happening, and some of the mitigation and prevention steps that you can take. So starting at the topmost overview, groundwater is the water below the feet. So it's everything that occurs in the subsurface, all the water that occurs in the subsurface, in the voids between the soil and the strata. So this groundwater originates from rain or snow. We just had that big snow event. When that melts, it enters the subsurface and recharges that groundwater body. Surface water can also recharge, so lakes and streams can recharge our groundwater resources. And so these are just two really generalized diagrams of groundwater flow systems, showing both an unconfined aquifer, so this superficial aquifer that is really tightly connected to the surface, and some of these deeper layers. And we'll be talking a lot about wells today. Wells are how we get our groundwater. So we pump it up from the subsurface to use for drinking water, for irrigation, and industry as well. And just a quick definition to make sure we're on the same page. I'll talk a lot about the water table again and again. So the water table is really the top of that groundwater body. So in the coastal zone, instead of fresh water on all sides, the surface water body is the ocean, and the ocean is really salty. And so you get this really dynamic balance between the land and the freshwater bodies and the ocean and the saltwater bodies. And so I'm going to step through a number of iterations of this diagram. So just to orient you, we have the ocean here on your right. The saline groundwater is indicated by this green shade, and then on your left is the land and this freshwater body in the blue. And so you can see what we call this freshwater saltwater interface. And so this is where that freshwater from the land meets the saltwater under the ocean. And this interface creates this curved boundary due to the buoyant forces between fresh and saltwater. So you think of saltwater has a lot of dissolved solutes that makes it more dense compared to the freshwater, which is more buoyant. And so that sits on top of the salt water, creating this freshwater saltwater interface. This is the only math equation I will show today, but we can estimate the depth to that saltwater interface based on the water table elevation. And so if we think relative to mean sea level, if you have a water table that is 2 meters above mean sea level, if this age is 2 meters, you can estimate that the depth to that freshwater saltwater interface is about 80 meters. So 2 times 40. And what we'll come back to again and again here, and why this is so important to think about, is that really small changes in the water table, so a ½ meter change in the water table, can cause a 20-meter change in that freshwater saltwater interface. I apologize for talking in meters. I should be talking in feet. And so this brings me to this definition of saltwater intrusion, which is the encroachment of seawater into our freshwater resources, leading to the salinization of our drinking water, as well as our coastal ecosystems, which you'll hear a bit more later on. There's a number of natural and human causes to saltwater intrusion. So starting with the natural causes, the first being reduced groundwater recharge. So this is again where I talk about the water table. When you have a drop in the water table, whether it's drought or well, we'll get into the pumping later, you can see this landward encroachment of this freshwater saltwater interface. Another mechanism is sea level rise. So sea level rise not only inundates formerly terrestrial land with saltwater, but also pushes that freshwater saltwater interface further landward. causing both lateral and this vertical intrusion of salt water. Storms are another driver of saltwater intrusion. I don't know about Plymouth, but in Woods Hole, we have had a lot of storms the past few months and a lot of storm surge. And so especially when you get high tides coinciding with these nor'easter events, you see saltwater intruding further into the land surface, whether it's by waves and sea spray or actual inundation from these really high tides. Even though it's brief, it can introduce saltwater into the subsurface and salinize these freshwater resources. And so here's just an image from Massachusetts during a surge event, highlighting that this does happen in our neighborhoods. So for the human causes, pumping plays a really large role in this freshwater saltwater interface and saltwater intrusion. So as you pump freshwater resources from this aquifer, you not only potentially get a decrease in the water table elevation, but if it's really close to this interface, you can get upconing and saltwater entering those pumping wells. And I just want to highlight that these coastal aquifers are incredibly important. So about 100 million people in the US in coastal counties depend on fresh groundwater. And so this is just a map showing population density in the United States. And you see this really high density along our coastlines, just highlighting the importance and really the reliance of our coastal communities on fresh groundwater. These are really generalized diagrams. Of course, in the real world, it's not this clean. And so there are a number of complicating factors that I'll just mention. First of all, it's really not a sharp interface, it's a mixing zone. And so one example to really highlight this is from the Biscayne Aquifer in Miami, which I'll talk about again a little later on. But here, this is a map of the subsurface. So it's a 2D cross section. So this is depth and then distance from the ocean. And these lines are indicating the salinity. And so what you can see here is that this freshwater saltwater interface is far from a line. At the base of the aquifer, it's actually a mixing zone 2 miles wide. Closer to the surface of the aquifer, it's a much narrower mixing zone on the order of 2,000 feet. Another complicating factor is geology. It's below us, we don't necessarily have one large groundwater system with different stratigraphic units. We can have different aquifer layers that create a complex geology in the subsurface and further impact where you have salt water. And lastly, there's dynamic forces on both land and sea. So our water table varies on a seasonal basis. So in the winter and in the spring, when you have snow melting, you have rain, groundwater tables are typically higher. You can probably saw that in the road driving in. But in the end of summer, when it's been fairly dry, there's potentially more pumping because more people near the coast, you see a drop in that water table elevation. Oceans are similarly dynamic, actually probably more dynamic, with tides that vary daily. They vary over 14-day tidal cycles. And the ocean actually also varies seasonally in terms of the level. So saltwater intrusion it's not just an issue in Massachusetts or not just something being talked about in Massachusetts, but it's occurring throughout the United States. So this is just a map, and the red dots indicate occurrences of saltwater intrusion. And so you can see this is an issue in coastal California, particularly Los Angeles, where you have huge population centers as well as irrigation, Florida, which we'll come back to, and some of these lower areas in the coastal plain of the mid-Atlantic. Thinking beyond just the United States, this is occurring globally. So we'll talk about different coastlines, potentially have different threats, but this is something that is not unique to the United States and is being talked about across the globe. And so I just wanted to quickly, I mentioned that I would bring up this Biscayne aquifer again, and I think this is just a really great example, is this aquifer is sort of the study case of saltwater intrusion, and it highlights change in a really short period of time. You know, as geologists, we think on really long time scales, but this is something happening at a relatively short time scale. And so here we're showing the extent of the Biscayne aquifer. And on these 4 plots here, this orange area highlights the extent of saltwater intrusion. So in 1904, this is one of really the first occurrences or known instances of saltwater intrusion. You see this smaller salinized area, but present as Miami became really an epicenter of development, a growing population. You can see with time this saltwater intruding further inland. So you can only imagine in 2020, if we had a map, it would be even more severe. So there are some approaches to mitigate saltwater intrusion and help manage the extent landward and the magnitude of salinization. There are a number of them. I'm going to touch on them all, but I'm just going to really talk about 2 of them. And so the first is probably the easiest to implement, and that's managed groundwater pumping. So really thinking about the aquifer system and thinking about how much you pump, where and when. So as this says, it's the simplest and most cost effective. And so as we think about Plymouth and potentially using this as an area, you know, we have high water tables right now. That would be a better time to pump closer to the coast compared to the summer when we have lower water tables, and shifting that groundwater withdrawal landward. As you can imagine, this also takes a lot of monitoring and a lot of coordination across decision-making bodies in terms of deciding when and where to pump. Another approach that is used currently in the West Coast is artificial recharge. So thinking about that groundwater table, when you have a higher groundwater table, potentially, you know, inhibits that saltwater from moving landward. And so you can inject water into the aquifer to actually increase that groundwater table and prevent that landward movement. So like I said, this is something being employed in Los Angeles. One issue is, where does that water come from that you're putting back in? And so you need a large freshwater source. This could be surface water, rainwater. Something that's increasingly coming into the conversation is treated wastewater or the very costly desalinized water. A few other approaches are subsurface barriers. So if you're thinking, yikes, expensive and difficult, you're right on that one. This is actually putting physical barriers in the subsurface. Difficult engineering and really hard infrastructure. There's barrier pumping wells. So if you have a well right at that interface at the bottom of the aquifer, you can pump out the salt water before it goes inland. But again, where do you put that pumped out water? It's all salty. And aquifer storage and recovery. So during periods when you have an excess of fresh water, actually pumping fresh water into salty areas, trying to store it there and pumping it out when you need it. Of course, there's mixing and that could cause other issues as well. So in terms of prevention, it's avoiding those potentially costly strategies. First and foremost are conversations like this. So educating a community, starting the discussion, integrating various stakeholders and leaders in the community into these conversations. And also, as Plymouth is doing, and David will talk about, is really understanding your aquifer and understanding the threats. So using the technology and the models that we have to really understand the aquifer system in order to better predict how it will respond with a growing population, changing climate, things of that nature. And so just to conclude, solar intrusion is really complex, and it's a growing issue worldwide. And to prevent and mitigate this intrusion requires coordination within a community, within a local, state, countrywide community, and coordination between scientists, policymakers, and the local community. So I have a question slides, but I think I'm going to pass it off to Dr. Michael before getting into questions, unless I'm wrong on that front. Oh,
Thank you, Dr. Guimond.
Share your slide now.
What's that?
So thank you, Dr. Guimond. Now we're going to have a brief presentation by Dr. Holly Michael, the Unidel Fraser Russell Chair in the Environment and Professor in the Departments of Earth Sciences and Civil and Environmental Engineering at the University of Delaware.
Oops, sorry.
Thanks very much, Frank. Can you all see my screen?
Yeah.
Great. Yeah, so I'm just going to follow on Julia's presentation and talk just briefly about ecological changes that are happening at the coast. Before I do that, I'll just mention that while I'm in Delaware, I do have ties to Massachusetts. I actually did my PhD work on groundwater flow into LaQuoit Bay and Falmouth, and while I was a student at MIT, and that's really where I developed my love of the coast. I came originally from Western Pennsylvania, and that led to, that was a while ago, so that's led to my career as a coastal hydrogeologist. And so, so I am familiar with your area, and I'm really excited to be here today and to talk with you about it. So I am a hydrologist, not an ecologist. I work with lots of ecologists and biogeochemists and others, but I'll just do my best to outline this issue of ecological change. So as climate is changing, our coastal ecosystems are in transition, as many of you may already know. With sea level rise and storm surges that are increasing in frequency and intensity, we have hydrological changes that are changing our ecosystems at the land-sea margin. So one issue is rising surface water levels. As the sea level rises, our surface water rises along with it. It just raises the base level. And that leads to drowning of the root zone. And rising sea level and surges also lead to flooding with saltwater, which of course affects vegetation, leading to loss of forests, loss of agriculture, and also migration of salt marsh, which is not necessarily a bad thing. But ghost forests or forest ecosystem transition have been in the media quite a bit lately, both locally, our Delaware News Journal, also New York Times articles, highlighting this phenomena that's occurring in many coastal areas. And so ghost forests, you can see probably best in the photo on the right, are where salt marsh is moving into to forest, to what was a healthy forest. The trees are dying, but the salt marsh vegetation is thriving. And so you're left with these dead trees that actually bleach out and look like ghosts. So here's a nice aerial photo from Time magazine. I believe this is coastal Virginia. And this is a photo from North Carolina. This is happening all along our coastlines. Another issue is problems with agriculture. So transitioning of the ecosystems in ag lands. We, especially in the Delmarva, but in other coastal areas, we have ag lands that are right up against the marshes or right up against the coastal zones. And so they're vulnerable to these changes. Again, this is making headlines locally to globally. And again, the issue is both flooding and also the effects of salt. So in this photo, you can see areas of the field that are essentially burnt out with salt. That soil is highly salinized if you take samples of it. And that's what a lot of our fields look like that we work in. So what are the key drivers of these changes? Julia already touched on this, as she emphasized more of the subsurface, the groundwater system. This is looking a little bit more at the surface. So here's a very shallow coastal cross section. This is a salt marsh, which is going to extend up approximately to the high tide line. And then in this case, I'm showing a transition into forest. This dotted line represents a storm surge or high tides. And when that happens, some salt water infiltrates into the subsurface, what was fresh water, and eventually, hopefully, flushes out. And then I mentioned how water tables can rise, causing some flooding conditions. So the and this, of course, can be ghost forests here, but also can represent agricultural change or other ecosystem changes. So we have both fast and slow processes that cause this ecological change. The main slow process would be sea level rise. It's occurring slowly over decades, although of course much faster in the recent decades. And so that raises the space level, it raises the high tide point and pushes everything essentially further inland. And then the fast hydrologic processes are these periodic high tides and storm surges that again push this the saline flood water up into the upland. So I'll just tell you about some areas where we're studying these ecological transitions. We have a project with the USGS and the Parks Service looking at 3 locations. Fire Island, New York, and Sandy Hook, New Jersey have maritime holly forests. It's one of the only, these are some of the last maritime holly forests in the world. So they're very precious ecosystems, and there is a lot of die-off after Hurricane Sandy. So there's a real interest in understanding the mechanisms of this die-off. And so we're doing work to understand really what are the mechanisms? Is it salinization? Is it rising water tables? And what can be done to save this important holly forest? Another place where we're working in that project is Assateague Island, Maryland. This time it's not a holly forest, but the loblolly pines have pine beetle infestations that are killing them. And one of the hypotheses is that that is due to salinity stress. So again, we're trying to understand why that's happening so that it can be prevented or at least slowed. We're also working at the land agriculture transition. This is an example of work we're doing in Dover, Delaware. This is the marsh along the Delaware Bay. We have lots of monitoring locations, wells, we're monitoring streams and marshes and irrigation ponds. And you can see this is the agricultural land. It's right up against the marsh. Behind it is the city of Dover. And so we're also dealing with issues of different water users causing seawater intrusion, potentially affecting the irrigation and these farm fields before the municipal wells are affected. And we have another project also on the Delmarva where we're looking at 3 sites that are paired agriculture and forested sites in Delaware, in Virginia, and in Maryland. And we see similar ecological change at all of them, though because they have different characteristics, because they have different storm events, they are slightly different. So what can we do about this? Julia already touched on some of this, but one, we're doing research to understand the scope of the problem, understand the mechanisms, and we're not only looking at the physics, the natural science of it, but trying to also bring in the economics, social feedbacks so that we can really predict future scenarios that include the human component, which of course is really important, as you know, thinking about reducing water use in Plymouth. I mentioned the monitoring water levels and salinity, but also we're looking at contaminant levels because as you have more flooding, as you have salinization, contaminants that are in the soil can be released, and that can also cause ecological problems. So the easiest example to think about is in agricultural fields, you have nutrients that are applied that are bound to the soils. If that is flooded, then those excess nutrients can get into our estuaries, cause algal blooms, etc. So what are the solutions? Well, we can always engineer something, right? We can engineer a structure, but that may not be, one, it may not be the most effective, but also not the best from a climate change feedback or ecological standpoint. So we're thinking about the use of green infrastructure. Julia did a study on marsh migration, and she published that last year or the year before, where she did an analysis of the benefits of allowing marshes to migrate into agricultural fields, because marshes actually mitigate flooding. So allowing them to migrate is a good thing for protecting the farmland, but also marsh migration is inherently a good thing. If we're losing marsh at the seaward edge because it's drowning, we don't want our marshes to shrink because they're such important ecosystems. They sequester a huge amount of carbon, much more than any terrestrial ecosystems, much more than our forests. And so it is a good thing, actually, if those marshes are allowed to move further inland, and that carbon sequestration reduces the feedback with climate change. And lastly, I think we need to develop science-based policies. So really understand the problem, understand the solution, so that we can make effective policies. And I'll stop there. I just want to mention that we have a lot of collaborations. These projects are led out of the Delaware Environmental Institute, but we collaborate with many different institutions, including Boston University. So thanks, and I welcome questions after the next presentation.
Thank you very much, Dr. Michael. Our final presentation detailing what our project seeks to accomplish locally and how will be given by Dr. David Boutt, our project scientific lead, full professor in the geology department at UMass-Amherst. Dr. Boutt.
David, I think you're muted.
Thanks, James. Can you all hear me now?
Yes.
Pull out the little camera.
This one?
Yes.
All right. Okay. Those of you online, can you hear us now?
I can, yes.
Yes.
Okay. All right. So we'll start over. It's a pleasure to be here, and I want to talk to you a little bit about the particular details of the project that we're working on here in Plymouth, really with the goal of trying to understand the potential magnitude of saltwater intrusion into the aquifer, but also to try to better understand the effects of sea level rise on kind of how the aquifer is working and how the aquifer interacts with really important surface water bodies. Those of you with ties to Plymouth, hopefully you understand the really important aspect of the water supply and the aquifer that is underneath our feet here. And it's really important connections to the community, to the ecosystem, and the people that occupy this landscape. And one of the really interesting aspects about what people refer to as the Plymouth Carver or the Plymouth Carver Kingston Duxbury aquifer system is that it's a very thick accumulation of very permeable sand and gravel deposits that are strongly connected to surface water bodies. All the ponds that are all over the landscape are essentially windows into this aquifer. And as we have impacts, let's say on from pumping for water use, or changes in hydrology, or changes in let's say sea level, it's going to impact all aspects of this system, not only from let's say a water quality perspective, but also how the ponds and aquifers interact with one another. So I'm going to show you a map in a second that is a product from the United States Geological Survey, where scientists there tried to map out if you were, let's say, in a pond, or you had a pumping well for a municipality or a house, where did that water travel or come from that was intercepted by whatever that body is? And these are called capture zones. So you can imagine this pumping well here is pulling water out, and it's capturing water from a footprint or a domain that kind of looks like that in cross section, or in plan view it looks like this. So this is the well, and this would be the area, let's say, of the landscape that's you're drawing that water from. You can also do this not only for wells, but also surface water bodies and actually the bays themselves. So what you're seeing in this map here is a map. So we're down kind of here-ish somewhere right now. And the different colors reflect the areas of the landscape that are being captured by different parts of the system. So in green are areas that are part of the aquifer that contributes to all the important ponds. Okay, yellow is water that's captured by, let's say, different streams or different ponds, and then drains to the surface via let's say the small percentages of rivers in the area. And blue are areas that are captured by wells. And one of the really important things about this aquifer system is that a lot of the water that makes it to the coasts, in this case Cape Cod Bay or Buzzards Bay right down south, is water that's actually flowing naturally out into the bay through the aquifer and not even coming up to the land surface. And that water helps kind of keep that saltwater interface at bay from encroaching. So if we start to change either sea level rise due to or the level of the ocean due to sea level rise, or if we change the aquifer levels by either natural changes or anthropogenic changes, as Julia mentioned, we can start to significantly impact those dynamics. So one of the colleagues of mine at UMass-Amherst have been working with the city of Boston to develop the best scientific understanding of what our future of sea level rise in this part of the region. And to kind of keep this simple for now, depending on how we emit CO2 into the future, we have very different scenarios of everything from a ½ meter of sea level rise, which we're pretty much already committed to, up to almost 2 meters of sea level rise. So that's over 6 feet. And one of the really interesting aspects of our region here is we're very sensitive to what happens with the West Antarctic ice sheet because of the dynamics of ice melt and the redistribution of water mass on the planet. We're really at the bullseye of sea level rise in this part of the world. So one of the important things that is, and Julie had mentioned this and Holly did as well, is that when the sea level rises, we don't only cause, let's say, surface flooding or inundation of the surface, we also have freshwater table rise in response to that. And there are significant examples of this in Hawaii, in southern Florida, and actually that building collapse a few years ago in Florida, some had attributed that to sea level rise and essentially the water table eroding foundation. So not only are we going to be facing issues of essentially inundated land, there's also possibilities for infrastructure, coastal infrastructure to be impacted. And this is something that the people in Beacon Hill, in my opinion, are not really factoring into significantly into kind of sea level rise impacts. So what I want to do right now is just talk a little bit about what we know about saltwater intrusion in the Plymouth Harbor and the town of Plymouth. We don't know a lot yet. We're working on it, but there's a number of factors that I think are give us some insight to kind of where the magnitudes of the problem is. One of the things that we have going for us is that we're in an area that receives quite a bit of natural rainfall. So there's lots of fresh water that comes into the aquifer that will help keep that freshwater saltwater interface at bay. Essentially, those buoyancy forces that Julia talked about. So you can see this. These are contours, essentially elevation of the water table, highest out here in kind of the state forest here, and then kind of push and move towards the coast. And actually, in this particular environment, we see almost 50% of all the water that falls onto the landscape actually infiltrates into the aquifer, which is quite high in an aquifer system. There's, as I mentioned earlier, there's a significant amount of natural fresh water that moves directly out through the subsurface into the bay. And here's an example of, this is a numerical model. I'll talk a little bit more. This is basically a simulation of how the water is moving through the landscape. Plymouth Bay here. So this is north. The blue areas are areas of the highest part of the water table. Red areas are low. Groundwater will flow from areas of higher elevation to areas of lower elevation. And if you look in this little below up here, all of these arrows that are pointing out into the white, which is the ocean, show that natural discharge of fresh water out into the bay, which keeps that interface, and most likely kind of even offshore under the bay. The current rates of groundwater extraction through pumping for drinking water, for other water uses, are actually fairly low relative to natural recharge. So that's good. And we'll talk a little bit more about that. In the case of certain parts of Cape Cod, Julia mentioned this kind of process of upconing. This is the red is salt water, the blue is fresh water. You can see as this well is producing water, it actually causes the salt water to migrate upwards because of the removal of that fresh water in response to that those dynamics. One of the other things Julia had mentioned is that the subsurface geology plays a really important role in how these systems function. And in the case of, this is an example from Cape Cod up near Truro, where they have some lower permeability units at depth that create some impacts in migration of the salt water into the freshwater system. And generally speaking, in this type of environment, if you have some of these units present, there's going to be, I think, more propensity for the migration of that interface. And there's in general a lack of these units present in our subsurface because of the way that the glaciers left sediment and retreated north. Although there is some evidence of some lower permeability units that we see up near sort of the main town center of Plymouth. So how do we improve our understanding of saltwater intrusion? What is the kind of the plan for this project? And one of the first things that we've all been doing collaboratively is collecting existing and new data on the salinity distribution. So essentially looking at, what the distribution of chloride or other dissolved sediments in the aquifer. And one of the things so this is some data that we've been working with, collected from, these are all the public water supply measurements of chloride in the aquifer. On this y-axis is frequency. So these are the number of samples collected versus the chloride concentration. And the drinking water limit is about 250 milligrams per liter. We do have some evidence of higher chloride concentrations in some of the wells, in particular up in the northern part of the town and across town. Whether or not these high chloride concentrations are related to saltwater intrusion versus other potential chloride sources from, let's say, septic systems or road salt, which is one of the big ones that still needs to be assessed. But generally speaking, as you get further away from the coast, you would expect to not to experience as much saltwater intrusion. One of the other important things that we're doing is we're trying to improve the understanding of where these different aquifer units are in the subsurface. There's some new, so here's a map showing Southeast Massachusetts here out to Cape Cod. All these different colors here are different geologic units that were mapped underneath Cape Cod Bay that give us some insight into the connections of these different offshore geologic units to onshore. And one of the really important things, there was a large glacial lake, a freshwater lake that actually was ponded here when sea level was a lot lower. Essentially, there's a big freshwater lake here that deposited a lot of fine-grained sediments, clays and silts that can actually be barriers for groundwater flow and actually have a pretty important impact on how groundwater moves into the bay, which could impact the distribution of saltwater intrusion. Here's a little cross section, like a slice through the earth, showing these deposits offshore. And one of the kind of new discoveries are the remnants of really old, like 10 million year old deposits that actually we think underlie Pine Hills, which is a new observation. We've been working with different types of geologic data, pulling data. Each one of these points on this map is a boring that recovered and described the sedimentary layers underneath the ground that we can use to help improve our geologic understanding. All of that information is going to be incorporated into a revised numerical model of how the freshwater and the saltwater in the aquifer interact. There's we're not starting from scratch, which is great. There's an existing groundwater flow model that was developed by the United States Geological Survey in 2009. That model was paid for by the state to help the towns that overlie the aquifer system, to help them manage out into the future their water supply. But this model was not developed to look at the interaction between the freshwater and the saltwater. So there needs to be some significant changes to the model, in particular to help us understand how the freshwater and saltwater is interacting. Again, this is a map showing the hydraulic head or the water table above the land surface, blue high, red is low, just showing you some of the fate of the groundwater as it moves out to the coast. So just to give you a sense, if you're not familiar with these things, essentially what we do is we split up the subsurface into blocks of different sizes, and we assign them properties, and we solve essentially equations that govern mass. We basically conserve mass, which is important, and we simulate how that groundwater moves through the subsurface, and we can make predictions of how that water is going to, what the fate of that water is, and ultimately how that water interacts with the ocean. One of the main challenges, or one of the issues in the existing USGS model, is it actually simulates water levels way above the actual domain. So this is the top of the earth here that shows the water table, you know, a number, I think in this particular case, almost 8 to 10 feet above the land surface at essentially here. If you were to look at this model where we're standing right now, would be almost below water. And so one of the things we're doing is to improve that model. That model was not designed to look at things happening by the coast, which is what we're most interested in. So just to give you a kind of a high level overview, what our project objectives are, we're assessing the impacts of saltwater intrusion into the freshwater aquifer, and also to try to understand how changes in sea level impact not only that process, but also how the ponds and the surface waters interact with the aquifer. And the primary tool we're going to be using is to develop a numerical model of how the system is working, with the goal of not only looking into the future, what could be some of the scenarios, but then help us use perhaps additional resources down the line in a more effective way in terms of monitoring, in terms of, let's say, collecting additional data that might help us understand how things might be changing. So we've been working on, and I'll show you an example in a second, doing some preliminary assessment of where the interface might be based on some of the simple calculations that Julia presented. We're refining our understanding of what's in the subsurface, and then moving towards updating that existing groundwater flow model. So this map here shows you just everywhere in the model domain, which is quite limited, where the water table is 10 feet to essentially 0 feet, right at the ocean depth. And so these are the areas that where you would expect to find the saltwater freshwater interface, you know, at relatively shallow depths below the ground. Okay, so it's kind of a preliminary look. And one of the things I think it's really important to understand is that because of the topography in a lot of the parts of Plymouth, especially those facing Cape Cod Bay, have fairly limited possible incursions of that interface because of the topography and the water table. But this map is going to change quite a bit when that simulation really takes into account the land surface and the water table. And with this revised model, what we're planning in year 2 is to look at different scenarios of potential saltwater intrusion and the impacts on of sea level rise, to understand what areas are most vulnerable, and then perhaps making some recommendations for how to improve the understanding of the system, as well as to perhaps rethink or think about how freshwater well extraction locations are managed. So I think one important thing that I think really goes beyond this particular project is just improving and updating the existing model that can be used to help manage the system, and one that that actually captures freshwater saltwater interactions. We will incorporate sea level rise scenarios into the modeling to try to look at both not only how sea level rise will impact how the interface, freshwater saltwater interface might move, but also the the hydraulic effects of that, and impact or provide scenarios looking at the impact on aquifer water quality in kind of these coastal regions. And then finally, some strategies and suggestions for mitigating some of those impacts, kind of along the lines of things that were discussed earlier. So with that, I'm hoping we can have a discussion and talk a little bit more. And yeah, I look forward to chatting with you all.
Thank you very much, Dr. Boutt. I hope what happened now is that you stop sharing and we can see the participants and have them raise their hands. You know, they're using that little model there to ask questions. I'll start off with the question, how will this study help the town or other agencies manage their water supplies, something of particular interest in Plymouth right now?
Hold on one second. Frank, can you repeat that?
Sure. How will this study help the town or other agencies manage their water supplies?
Hey, Frank, can you repeat that? I'm sorry.
I'll try again. Can you hear me okay?
Yeah.
So one of the questions in this area, we're concerned about conserving water in general, is how this study might help this town or other agencies in the town or nearby manage those water supplies.
Yeah, I'll start, and then Julia or James or Holly can chime in here. I think one of the first strategies that Julia brought up was reducing your water supply or reducing water use is like kind of the first line of defense, right? And I think part of what we're doing in this project is really kind of alerting the community to the potential risks or to some of the issues surrounding saltwater intrusion. And I think that in itself, I think, is an important first step of communicating, okay, what are some of the issues, and then thinking a little bit about, okay, how can we manage the water use or the water consumption in the aquifer in a way to help us mitigate impacts. I mean, one of the things that is happening already within the town is a lot of the water that is produced from municipal water supplies is actually returned back to the aquifer through either treated wastewater discharge or through septic systems. So that in itself is actually a good thing. Now the question is, some of where that water, we had a discussion about this yesterday, somewhere that water is pumped is not necessarily the same as where that water is put back in. So understanding some of those, that redistribution of that water, I think is important to perhaps predicting what could happen. But I think in terms of raising the awareness of the connection between how people are using the water in the aquifer and what that means for saltwater intrusion or potential for saltwater intrusion is important. I don't know if Julia or Holly or.
I mean, I would add one small thing, which is that, I think that the model that David is developing is a really important tool that not only will allow you to evaluate the benefits of reducing water use or different strategies that you might do, right? Because you can put it into the model and see how that changes things, but it also helps to identify areas that might be most vulnerable so they can be really targeted for mitigation.
Right. And I think too, there's a lot of, whenever I talk with you all, and rightly so, there's a lot of concerns about, the really important freshwater ponds and wetlands in this region, and the interconnections between those systems and the aquifer and the municipal pumping is important, and how how to maintain the high, the water quality levels in those systems going into the future, I think fits into that well too.
I don't know if you, Mr. Justice raised an interesting issue, a very local issue, and I'm not sure how it will relate to what we're talking about today. Although it's a water issue, it's a water pollution issue, and that's concern with people in the community for the use of Cape Cod Bay to dump low-level radiation from the former nuclear plant into the water. I guess somehow address the how that may or may not interact with the the same sort of systems.
Yeah, that's interesting. I'm only a little bit familiar with it, but I think I would imagine that because of all there's a strong offshore kind of focus of freshwater discharge into the bay, that any possible kind of recirculation of, let's say, some of that water from Cape Cod Bay into the freshwater aquifer would be pretty limited. I mean, obviously, Julia talked about these kind of dynamic forces. Essentially, as the tides go up and down, you can force, ocean water into the aquifer at those different scales of the tidal. But I think that would be pretty limited in terms of impacts of, water that is being used by the community. Not that being said, I think, there's still perhaps, some risks to the coastal, to the coastal ecosystem and other shellfish industry and other aspects. But
Yeah, that's kind of a tough question.
Yeah.
But
I mean, we know in tidal systems that there's exchange, right? As we go from low tide to high tide of tidal water into the very, very marginal part of the coastal aquifer, but a lot of that is that water is flushed, on short time scales.
so I'm not seeing hands raised, and you can, if you're not familiar with Zoom, there's the ability to make a little artificial cartoon hand raised to ask a question. But I'll ask another one that was.
Hey Frank, we've got an audience member here.
Okay, great.
Yeah.
Great.
Yes.
Hey, thank you for the
Yeah.
great presentation. It's really fascinating. Is there been any cooperation or communication with Mass DEP about what you're doing, especially with some of the issues of water withdrawal programs?
Yeah, in the sense of some of the initial discussions, at least from my end, and I'll let.
David, can you repeat the question? Sorry.
I'm so sorry. Yeah, I'll repeat it. So was there any, have we had discussions or interactions with Mass DEP, especially in light of that they're the authority that permits public water supply or public water use? And so kind of the short answer is we've been interacting with them on more on the data side of getting data from like public water supplies, not only water use but also any of the chemistry or the data that they ingest from testing. I think it's definitely something. I think as we move a little bit farther along in the project, I think that's in the plan to be connected with them. I don't know if Frank or I don't know if Hampton or anybody else is on the line that can comment more specifically. I think the folks at the DEP that I'm aware of, they're kind of following along on kind of what we're doing, but not quite there to kind of have the conversations about how, some of the things that we find might impact, what they might be interested in. We've been working with some of the local consultants that work with the town of Plymouth, work with the town of Wareham on, from more of a like water supply development perspective. And I think there's a lot of interest on their end, because they're going to be ultimately the ones that are going to be trying to help their clients, the towns, find water supplies that are the most sustainable on the face of these different challenges. So it's a good point. I think it's something that we'll get there eventually.
I mean, a tag-on question to that would be whether, and we've kind of said that this groundwater model that you're working on, when it's done, will be a very important component of the overall project. So the question is it's going to be available for others to use, correct?
Yeah, so the plan would be that it would, it would live in the public domain. And I would hope that it would be something that that different entities might be able to take advantage of, for sure. Frank, I think there's somebody, a few people online that have their hands up.
Oh, really? Okay, I can't see that. Just a second.
Speak up. Speak
Yeah,
up.
hi. Can you hear me?
Yeah.
Yeah, okay. I encouraged by what Holly Michael said, that the one of the solutions to this problem is engineering, building structures. And there's an architect that's close to my heart. I proposed the elevated city, so-called a study for elevated city, because according to the scientists who predicted a 4-level sea level rise by 2050, it's inevitable that nothing can stop the sea from advancing. The federal program of the managed retreat is not working either, because people don't want to relocate to higher ground. So it would be nice to do the new development above the sea level, because the sea is going to advance no matter what we do, right? So can you comment on that?
Yeah, this is a really good point. I think, a lot of it comes down to economics. What are the different technologies or approaches that can be used to address the problem? Well, one, what are the problems, right? Is it salinization of the water supply? Is it flooding of the land surface, right? What are the problems that could be pushing people out of where they're living? And so that's going to determine what the solutions are, because a surface structure may not work for seawater intrusion that's happening underground, right? So it depends on the problem. Yeah. And then it depends on the expense. And, so there's going to be economic implications of whatever is decided. And so I think that's why it's really important to bring in not only the science and the engineering, but also the economic and policy side to think about what's the best route.
That's what I mean. So what the idea is to, instead of retreating to high ground, we should attack the ocean, as many countries are already doing around the world, right?
Yeah, it's true. I mean, yeah, you look at the Netherlands and they've been engineering it for hundreds of years, right? But there are implications to doing that too. Think about Louisiana, right? It essentially causes the land to sink. And so it's important to think about the whole system, I think, and in designing approaches to it.
Yeah, and Frank, one more little question to David Boutt. David, as you may know, the Massachusetts prohibits the construction of sea walls new seawalls. So in Plymouth, we built a new seawall at the Long Beach, but called it repair. Okay, basically, what we are facing here is we need to change the state laws if we want to at least temporarily stop the advance of the sea level.
Well, yeah, and I think as Holly had mentioned too, those structures might be relevant for kind of the surface inundation, but they don't necessarily capture or prevent kind of the subsurface part of that process.
Yeah, actually, if I maybe add to that, sorry, David, but because the pressure propagates underneath the structure, right? So if the structure is going to help you with the surge, but the structure is not going to help you with the rising pressures from sea level that are going to push that saltwater underground further inland. And that's the issue that they have in the Netherlands with, they have these polders, but even though they have barriers, the surface water is not getting over. They're still getting saltwater coming up from below. So that's a concern.
Yeah, so all our revetments that we are spending money right now is only temporary.
So is there anyone in the audience that has a question? I have one from someone online.
I think Jerry, or I'm just seeing the name Jerry Williams had their hand up.
Okay, Jerry.
Yeah, hi, Don Williams actually here.
Oh, okay.
David, you've done some studies for us before, and I'm familiar with your work. My question is, and I'm looking probably further down the line than you want to think about, but how are you going to take this information to the legislators who have power to either say yay or nay to solutions that are suggested by science? I mean, legislators don't exactly have a great record with dealing with science in a positive way.
Yeah, I've been dealing with it for 15 years in this state. It's a challenge, but I think what I've learned is it takes a lot of different pathways to do that, by working with people like you, by getting the message out and building community support and building it from the community. Because we can produce these plots and figures and things like that, but they need to be digestible by the citizens. I mean, it's been difficult enough trying to get the board of select people to pay attention to some of the work that we've been doing so far, right, Frank? And I think it's going to be a challenge, but I think it's also something that I think working all the different angles with the community, but it's something to think about for sure early on.
Well, we will help. Green Ponds Watershed Association will do what they can to help. We believe in you, believe in this. So keep us in mind.
All right.
So I have a question online from Guimond Panthi, and it is directed to Dr. Michael. He's particularly interested in the ghost forest issue and knows that with the sea level rising, the water table also rises, making an unsaturated zone saturated in nearshore aquifers. What factor is more sensitive for coastal vegetations in general? And are there any studies on it, any success stories in restoring ghost forest, bringing them back alive?
This is a great question. So the short answer is we don't know. A long answer is it partly depends on species. So some species are more salt tolerant than others. Some are more tolerant of having their feet wet. It sometimes depends on how long they have their feet wet, meaning there's not much unsaturated zone or the roots are in the saturated zone. So that is one of the big questions of our studies, or especially the USGS studies with the holly forest and the pine forest, is trying to use our understanding of where the salt goes and where the water table's shallow. We have decades of data on ecological data on these forests. So ecologists going out every year since the 1960s, recording the vegetation, die-offs, things like that. And so our hope is that by using models like what David showed, we can figure out which areas had high water tables, which areas were more salty, and compare those with the areas that died off, so that at least for these forests, we can better understand what the major driver is. And that would help us to figure out how potentially to mitigate it. Hopefully, does that answer your question? Frank, I think you're muted.
I'm not sure that Guimond is still online, but it was a good thorough answer, and he can look at the recording.
I see him. He's
Oh,
there.
you do?
Yeah.
Oh, okay, I can't.
Yeah.
I think I'm not seeing everything. I don't see any hands, and other people see hands raised. Is Linda Lancaster available to? She has a question. Linda, are you available to come on and ask your question?
Yes, hi, I'm Linda. I just wonder, do we know if salt water is currently intruding into any private wells at homes near the coast? And is there like an acceptable level, of salinity? And if someone has that problem, what do they do? What's the fix?
So there's a group of us that are working with that are trying to do some surveying and to collect data. Off the top of my head, I don't know. And Frank, if we've found any private wells that have had salinity issues, if you get above 250 milligrams per liter, which is the secondary contaminant level for, let's say, chloride, that drinking that water for a certain amount of time, over longer periods of time, can lead to hypertension and some health issues. So, and if you think about it, the salt water has a chloride concentration close to like 35,000. So it's a very small amount of salt water that can actually cause your freshwater quality to degrade. Frank, I know there have been a few cases that you guys have come across where there's been some pretty high salinity levels, right?
Well, we haven't had it verified by the people who should know, but we've done studies right here in Center Hill where our headquarters is located. And the highest salinity was found from the well at our headquarters.
Yeah, don't drink the water.
Oh, no.
Yeah, so we've done about 12 homes in the general vicinity, and we're, in a very coastal area. This is the area that instigated our first interest in saltwater intrusion, because we saw changes in a freshwater pond that's very close to the beach. And look at old maps, it used to be several hundred yards from the water, and now it's maybe 50 yards from the water, and it's being impacted on a daily basis. We see the water, the surges overcoming the dunes, and we see the salinity going up. So that instigated our investigation and our interest in saltwater intrusion. So then we had our interns use, now we haven't had this verified, but they were using those basic instant total dissolved solid salinity and well, 3 factors. And they did 12 homes in the area, and of course they did our own, and we were the highest. So we're waiting for the scientists to tell us, and we take double samples, one they take instantaneously, and one then you archive. So we haven't had those verified yet, but we have a very interesting well too. I'm not sure, we're sitting probably the highest point on Center Hill, within very short distance from the water, and so our well is starting high and probably going down to a particular level. It would seem to be maybe prone to it, but I'm not sure. So
I think, Julia, did you have something to add to that?
Yeah, I just thought that was oh, it's just a really important point that I also data, but there's sort of a bad side to that. If you have
Can't hear you.
I'm not hearing that too well. Could she come
Yeah.
closer to the microphone at the center?
Well, I wanted to make the point that, well, private wells can be very useful. Reporting of salty wells can impact your house price, right? If you have a salty well, you don't necessarily want to tell the world because that impacts your house value. So there's a double-sided, whatever the saying is, to report it. And so I don't have a fix for that. I think, a better reporting system would be huge in terms of tracking, especially in these coastal communities that do rely on private wells. But whether people are going to report or want to report or just going to put a desalinization system in their house, which I've seen, is a whole different thing.
I said we had a presentation yesterday, and I said one of the interesting things we've come across, and we've sent out several hundred letters to coastal well owners or who we think might be. And the general response for those who have contacted us directly or we've actually gone out and interacted with them has been very positive. So in this day and age, when there's a lot of distrust of government or other entities, I've been very pleasantly surprised because I think people understand water to be a unifying theme that we all need to be concerned with. So for the most part, they're overcoming their suspicion or concern and being very willing to have us take samples, even in the midst of the winter, even coming into their homes. We hope that holds true as we go out and do dozens more, but I think people understand natural resources now more than they used to as such an important issue for us all.
You're not.
To manage the questions. All right.
So do we have other questions? Again, I can't see hands.
I've
There's
got
a question in person who hasn't.
Is there anyone that has not had a question answered?
Holly, I think you mentioned about the expanding of marshes and it being a good thing, of course. I'm sorry, I can't remember. But early on, we talked about the natural mitigation measures as opposed to these massive engineering ideas. And so expanding marshes is one idea of a natural mitigation measure. Can you give me some other ones? I mean, did you mention reducing water consumption? Would you consider that a natural mitigation measure?
So I think if I heard the question, you were asking about sort of natural versus engineered mitigation methods. And what's that?
What are some more natural mitigation?
What are more natural? Yeah. So again, I think it depends on the problem. So for the surface salinization due to storm surges, marsh migration, but also there are green infrastructure solutions. So designing, designing vegetation, designing the land surface, right? So you can design you can put in natural things that will help to reduce the surge flooding. But the subsurface is hard, right? The subsurface seawater intrusion, the surface barriers aren't really going to help. And so I think the main natural solution there is just to reduce water consumption and also to think about where water is being extracted so that, because the seawater intrusion is going to depend not only on how much is extracted, but also where it is extracted. And so again, that's something that David can do with his model, thinking about smarter ways to manage the system to reduce the seawater intrusion. Julia might have some other ideas on that. Julia, do you?
I can just briefly add to the surface mechanism. So this would be thinking about storm surges. Really, the role of vegetation is to create as much roughness as possible, because that actually provides friction and holds back that surge. So in different areas, they're trying to rebuild oyster reefs in the coastal ocean, provide a lot of roughness, as well as a number of other water quality improving factors. And so that is one mechanism. Seagrass beds are hugely important for both water quality and that roughness factor. And then you can get into the marshes in the coastal forests as well. So there's a lot of strategies in terms of putting structures in that oysters will actually, can start to build off of these new oyster reefs. And of course, the best mechanism is a little bit of everything.
So we have a question. We have a question from Judy Boutt, a member of the Indigenous Resource Collaborative, which is one of our partner groups. Judy, are you able to?
Yeah, let me give it a whirl. Can you hear me?
Yep.
Okay, well, what I want to be able to do with young people and actually have them share it with a variety of ages is to do some 3D models, building actual, hands-on. I don't know what the materials will be yet, but you can imagine what could go into something like that, I'm sure. So what my question is does a site come to mind? Having the beautiful graphic maps that you showed is inspiring this really, but I want kids to be able to take it into the more concrete realm and really understand by building them, understanding these sites. So would you recommend a particular place, or should we maybe make a more generic kind of model, just incorporating different elements?
Yeah.
So that's the question.
Okay, so that really cool question. Yeah, we've had here at the center, they actually have this nice 3D printed topographic map that I was just thinking about when you were asking the question. The 3D printing has really taken off, and I think there's some really cool things that we could do to like either create like almost, I was just thinking like, could you have like some building blocks or something like that, where you have like different layers and maybe ones that have like different position of the saltwater or freshwater interface. One of the things that I do even in my university classes is we have these what we call sand tanks. They kind of look like an ant farm, and they're like two pieces of plexiglass with like sand and gravel in it. You can actually have, I think James yesterday showed, and I don't know, Julie, you didn't, I don't think you had those images in your presentation, but basically you can have like these physical scale models where people can visualize the interaction between the saltwater and the freshwater. If the saltwater was like dyed red or some color, and it could differentiate it. So there's some, I think, different ideas, more static things we could try, but also, some dynamic things, maybe even having one of those sand tanks here at the center where people could like use and explore. They're really fun to play with. So those are a couple things off the top of my head. I don't know. Yeah. So Julia was mentioning that you can actually do like little simulations or experiments with these things, and I do that in my hydrogeology classes, and I don't know, Holly, you probably have some similar experiences too.
Yeah, and we've done it for outreach for younger kids too, and they find it really interesting. So you can inject the dye down the wells and things like that and watch it move through.
Do you have any photos of some of these different versions that you've done? just informally?
Yeah. Judy, if you send me a message, or I'm sure Holly or James or Julia too. But yeah, and there's actually some nice off the shelf products too that you can buy from, some of the different scientific education outfits. And that's also nice too, because you don't have to make it from scratch. But I think having like, what I would like to maybe try to make is like some solid 3D printed model, I think, of something. I think that would be cool to do too, like kind of hands-on. Yeah.
Great.
We had
Thank you.
a 3D model at some point where I think we had flooding go up, but then you can't really see the salt in the subsurface. But I don't know, Julia, do you remember that? Did we have a 3D model?
She's shaking her head.
That's her.
That's before your time. Okay. But so I think it is potentially possible also to have some dynamics in 3D, but then you can't really see the subsurface.
Yeah.
I would
Great.
add, depending on what your budget is, you can also build these 3D models out of clear shoe boxes. And you can kind of attach little, kind of like soap pumps to the tops of the shoe boxes. And similar to what the other folks said, you can add dye in there. You can watch water move through the shoe box, and maybe that would be better suited for a younger age group, but something to keep in mind too.
Great. Well, one goal would be, one of our missions is building, real sense of connection to the parts of the environment that are involved here, water particularly. And I think one of the really powerful ways that this could evolve is for kids, Native kids that we're working with, other kids, to do some of these models and then explain them to older people that don't know yet about this, that haven't gotten involved in it. And I think that next step, that next expression, communication level is something I really want to make sure, to pay attention to and build in, because I think that having tried to convince adults of certain things over time, but recently about some of the issues going on in Carver, Plymouth, Wareham, in terms of sand and gravel removal, the destruction of the pine forest, and Plymouth, of course, and seeing adults' eyes glass over even, all kinds of people that I expected really understand it. So that's why I want to set up some intergenerational exchanges.
Yeah, great, Judy. Thank you so much.
Thank you.
We've got a question here in the audience.
Hi. We have a junior garden program that is, because I'm in a garden program, we went to the schools. And we always talk about the sole source aquifer that's under Plymouth and Carver. So my understanding that the water is all connected, underground. So if people here are having salt in their water, all in the whole aquifer, why would it just stay in one spot?
Okay, I'm just going to repeat the question so people online can hear. The question is, so underneath the region is a sole source aquifer, and it's connected regionally across the landscape into the ponds and the aquifer material. And the question was about if people are having, let's say, issues with salinity or saltwater intrusion on the coast, why isn't it distributed all throughout the aquifer? And one of the explanations for that is because as I showed those maps that had those like flow arrows. So what happens is the water that comes and falls on the land surface, like up by Miles Standish, for example, that water moves vertically through the ground, it reaches the water table, and it then moves laterally. So that fresh water is actually pushing it's moving the water molecules, the actual water through the ground, and is actually counteracting the movement of the salt water through the ground. So it's almost like a conveyor belt. You know, you got water come in and it's coming out. Now, when things happen from natural causes or anthropogenic causes, you can disturb that balance, and that balance is what Julia was describing. And some of that salt water can come in and mix and start to pollute or contaminate the water, but it tends not to go very far laterally into the aquifer because it's being counteracted by the new fresh water, let's say, that's coming through the aquifer. Yeah. So it's just kind of pushing that out. So, you know, there are, Julia showed that example in Florida where at the toe, at the bottom, you can actually have a lot of encroachment. So what's kind of cool is, interesting from a scientific perspective, is that, you know, as you go deeper into the aquifer and actually farther away from the coast, you can actually have more intrusion, but at deeper depths. And sometimes, well, you know, in our particular case here, we have, let's say, 150 feet of sand and gravel on top of bedrock, and the bedrock itself can actually help the bedrock, like the granite that you see around here, tends to be fairly low permeability. So that actually helps, I think, limit that process here. But that's something to be explored, I think.
I think we're reaching the end of our memory on our Zoom call here. If anybody has anything specific that they want to answer to right now, otherwise you can, and our guest academics will, I'm sure, respond to specific questions that we can forward to them. You can send them to us at SEMPA. Is there something that is really pressing before I wrap it up? So I'm just going to move ahead with that and say a recording of this event will be available in the next day or so. If you wish to access that recording, please call the Pine Barrens Alliance at 774-773-9982. Leave your name and email address and we'll send you the link. The task force, I want to note, is close to beginning sampling of wells located in key coastal areas. So if you're interested in being trained to assist in this specific effort, again, contact SEMPA. Research and a variety of public events associated with this state-funded MVP project will be ongoing for the next 2 years. To stay abreast of those activities, visit our Facebook page, Plymouth SWI Task Force, or call the number I mentioned before. And finally, to Doctors Boutt, Michael, Guimond, and Heiss, excuse me, on behalf of the dozen partners of the Plymouth SWI Task Force and everyone here today, thank you very much for a very instructive 1.5 hours. It's really been a very positive step for this project, and I think for the community. Thank you very much.